second is QuickSort. Okay, so let's just have a quick look over them. So what we do in MergeSort is, let's say we have this array which is basically not sorted. So what we do is basically we try to divide them in half and half, let's say equal portions or equal subparts. So here we have 13827, we have 4310, then we divide again 3827, 43 and 10, and while like grouping them together again, we sort them. So while grouping them together, we'll sort them as 2738. While grouping them together, we'll sort as 1023. And while grouping these two pairs together, we'll sort them. Okay. So basically what we do in simple words, we first break them down, and when they are in a single units, we simply merge them or add them, group them, whatever you want to say. But while grouping or merging, we ensure that they are in a sorted order. Okay. So we break them, and while grouping, we take care of this, that they must be in a sorted order. Okay. So let's see this code. So this is MergeSort. Okay, we have defined, taken an input n and size, we defined the vector. Okay, so here we are calling MergeSort on 0, start index, last index, and our vector v. So this is the function for MergeSort. Okay, we have made the base case as if start is equal to n, basically single value, just return this as vector v of start or n, doesn't matter. If there is difference 1, basically there are 2 cells or 2 units. So what we will do, we will check that if end is greater or start is greater, basically which one is greater. Okay, see if the start element is greater, just swap it. If the next, like start means first element is greater, then swap it. The second element is greater, no need to swap. It's simple. You can think of this part. This base case is for single cell or single unit, and this is for 2 units or 2 cells, you can say, or 2 indexes. Okay, and what we're doing here, we're defining mid. And mid in the same way we do in binary search, mid is equal to start plus in minus start by 2. Okay, and now we'll call recursion on left and right part. Okay, start from start to mid, and then mid plus 1 to end on VV. And now what we are doing is we are simply merging them. Okay, so we are here breaking them down to 2 parts, and later we are merging them. So, and what we had to do here is, however, let's say when we are merging, we actually have two sorted arrays. Let's say you are at this step, you have 2 sorted arrays, you have to get a final array which is also sorted. So think, how can we do so? So you can think you have already solved this kind of problem. Let's say there are 2 vectors, vector A and B, and they are already sorted. Let's say we got its size. Okay, we define a new vector or size, their addition. Basically, let's say here we have 2, then final will be 4. We simply added them, and we kept the 2 pointers I and j on these 2 arrays. Like here a vector pointer I, here pointer j, and simply compare them here, and simply compare them. Like we have already solved this problems as some problems, like very small problems. It's like we have two sorted arrays, and we have to merge them. How to merge 2 sorted arrays so that final array is also sorted in such a way. Okay, so this is the kind of sub problem you can think. So we have done this. So okay, so we have the answer. So what we did is we called the MergeSort on entire array. Now we define a base case. We define a mid. Mid means how we are dividing the array, and we call recursively on left and right, and later we merge them. And we find the function for merge, and what we are doing in merge, basically we have 2 vectors, 2 sorted vectors, and we simply merge them while ensuring that the new vector we are getting is also in a sorted manner. This is what we do in MergeSort and what we have in MergeSort. So try to check its time complexity and space complexity of what we did actually here. So I copy paste my entire code. So if I try to write this recursive function, is what we have is tn, 2 times of t and n by 2. Okay, and this is the merge step. So there is a order of n, and when we use the Morse theorems, so we can write this as n a b a. So our b is 2, our a is also 2. So we will get an order of n. We'll get it in an order of n, and when we know that if these 2 cases like fn, this fn part, if the same order n and the c is also order of n, so these are same, so we'll have answer as c log n, and c is simply n, so n log n. So our time complexity will be n log n. And if we go for space complexity, so 1 will be the order of n for the merged vector space because we are defining it here. If a new vector space, order of n will go there, and we are calling these things recursively, so it will be some log n, depth of recursion is log n. So we are simply going to add them. So and we, after adding them, we'll get O of n, big O of n. You understand these two parts. Okay, so we basically use the master theorem to get the time complexity, and for the space complexity, since we defined a vector there, so the space required will be big O of n, and the recursive call like stack functions, it will be log n, and when we add them, obviously we go for big O of n. So now we have QuickSort. So QuickSort works on the principle of divide and conquer. We are simply taking a big problem and dividing into smaller problems. Okay. So here what we have is, let's say an unsorted array. So what we do is we define some pivot element. Okay. So and we ensure that pivot element goes to its right place. What we mean by right place is, see, if we here our pivot element is 5, so 5 is right position, that all the elements are smaller to it or on the left, bigger to it or on the right. So we pick an element, call it a pivot, and we put it at a place to ensure that all the elements smaller than it goes to the left, all the elements bigger to it goes to the right. Okay, let me show a better example. So this one, let's say this is the unsorted array. So we call this as the pivot 40, and by the end, what we do, we ensure that the 40 move their position where all the elements smaller to it goes to the left and all the elements bigger to it goes to the right. That's that simple. And we do the same for the left and the right array. So what we have to do first, we have to define a pivot element. Okay, we have to define a pivot element. Let's say the last element pivot element for us. And what we do, we will partition around this pivot element, and we'll move the pivot element to a place such that from there all the elements left to it will be smaller than that, and all the elements right of it will be bigger than it. Okay, like this. So the 40 is the correct position. Let's say if we assume we have sorted it. So if you will surely find that 40 is at the correct position. So this is what we are doing. And for 40, all the elements to the left of it are smaller, and all the elements to the right of it is bigger. So that's the method. And do the same for the left array and the right array. Okay. So let's just check the code of this. We have QuickSort. Okay, we call the QuickSort on the vector v array. Let's say starting position and ending position. If start is greater than end, for this only, we define a function partition, and we call the QuickSort on left side and right side. Okay, left array and right array. So just understand what is the partition. So this is the motion. We have to just understand how we are moving the pivot element or how we are placing it. So this is our partition function. So first we get the pivot element. Okay, we are setting the first element as pivot. In the GFG, it kept as the last, and it doesn't matter. You will see that choice of pivot. Always pick the first or last or random element as pivot, or mean or median. Like, not when we do median, not mean. We have to think of, can we do mean? No, because it may or may not lie in that array. Okay, so we define the pivot, and it's like a two-pointer concept. So we define I at the start plus 1, and we j as the end, and while I is less than equal to n, and v of I is less than equal to pivot, then I plus plus, and when there is some element bigger than pivot, then stop there, sort of that I, and do the similar thing for j, and then you will stop it. I don't understand this part. This is part is simple, intuitive, but just think of this part. You can write this code in other ways also. You just need to ensure that our pivot element go to the right position. And what is the right position? That all the elements to the left of it must be smaller, all the right of it must be bigger than it. That's only this part. Okay, this is simple. Yeah. So we call the pivot function QuickSort. Sorry, not pivot function, QuickSort. So on QuickSort we have the vector start end, and we define the partition, and then we are calling QuickSort on the left array on the right array, and this is the partition, and here we are still returning the pivot index first, because before the pivot minus 1, this index we are getting is the left array and this is the right array. So you have to think of this part. Okay, just code by yourself. You will learn a lot in this. Now let's move to the time complexity of this. Okay, so it's the same way here. We have the recursive function the same way. So our time complexity will be n log n. But here basically we are not defining a vector or anything. Everything is in place. So the space complexity will be O of log n. But the worst case of recursive that will be log n. Okay, O of n. But we can go for O of log n. But when the case is skewed, see now version are skewed, it might go for O of n space, big O of n space. Okay. So now let's just see the difference between QuickSort and MergeSort. This part is important. So I'll just see the worst time complexity. For QuickSort it goes to n square. For the MergeSort is always n log n. And in MergeSort the array is partitioned just half, like n by 2. N by 2, n by 2 plus 1, it's very close, like just a difference of one cell. But here in QuickSort it's not the case. So we do some random sorting, like the partition may not be of equal sizes. Okay, and we don't require additional space for QuickSort. It's an in-place operation, but for MergeSort we require extra space. Okay, and so this sorting method is internal and external, stability, not stable, stable, and this is important, preferred for array and it's preferred for linked list. Okay. We also think of this part which don't require external array space, it required an additional space. Okay. I think the main thing is to remember these two parts, how we are part testing, and you already know them while understanding the algorithm. The main thing is to remember the time complexity. The worst case goes to n square, and with the n square, let's say the array is entirely reverse and we are picking our last element as the pivot element. Just try to think of this part when the complexity will be n square, and for MergeSort we will always have n log n. Okay, so that's it for today. See you on another day. Bye bye.